All right, let's talk about plotting polar curves. This can be a little bit challenging, so take a deep breath. Let's go over this together. Whenever you have an equation that says either r equals some function of theta, or sometimes all r and theta are on the same side, and it equals 0, or maybe equals 5 or something, it doesn't have to equal 0. And if it doesn't equal 0, you can always move whatever number you have to the other side and get it to equal 0. But the point is, if you have an equation involving r and theta, that's all these two equations are saying, you want to graph this polar curve, which will be the set of all polar points r and theta that satisfy the equation. So all polar points that you get, all thetas and r's together that satisfy this equation, are part of the graph of the curve. Okay? So usually the most basic way to plot such curves is by building a table of coordinates, getting a bunch of thetas, plugging into the equation, finding the r's that give you the thetas that come from those thetas, right? And then plotting those points on a polar grid and getting whatever the curve looks like. So let's do this simple example here. I would get, by using this table, I would take r equals 0, theta equals 0, plug into this equation r equals 2. What will I get? There's no theta to plug in, so I get 0, 2. 0.02 is me looking in this direction and moving 2 units. So this is my point. When theta is pi over 2, I'd be looking up like this. And then what will r be? R will also be 2, because when I plug in theta equals to pi over 2, nothing changes in my equation, so I'll be moving this way. When I plug in theta equals pi, I'd be moving this way, because I'll be looking to the left and moving 2 units. So all of these are going to equal 2. And in each direction that I look, I'm going to be moving 2 units away. More than that, even if I plug in numbers in between those angles, so pi over 6, 30 degrees, 45 degrees, even 31 degrees, and 65, 67 degrees, I always get points here that are 2 units away, whatever direction you look at. So at the end, this is going to plot a circle as I do that, right? I think I can make a neat looking circle. Let me see. All right, I got it. It's a great circle. This is how to plot this curve. But also look at what the problem says. Obtain a Cartesian equation to check your work to see if this actually needs to be a circle or if it will actually be a circle. Remember, from polar coordinates, r squared is x squared plus y squared. So if I start from this equation, say r equals 2, I can square both sides to say r squared equals 4. And then remembering that x squared is r squared is x squared plus y squared. So x squared plus y squared is 4. So this exactly predicts or confirms what I just found, which is that this is a circle centered at the origin or at the pole with radius 2. So all of that makes sense so far. Look at how much simpler this equation is when compared to this one though. This one has a bunch of squares and stuff. This is just r equals 2. So the simplest kind of equation for a circle would be in polar coordinates. I think that's pretty cool actually. Circles behave really well under polar coordinates, much better than in Cartesian coordinates. Another equation that you have over here would be something like theta equals pi over 3. This is another very simple equation. How would I possibly plot this if I try and use this table of coordinates that you see to your left and I plug in theta equals 0? I would get 0 equals pi over 3. That is not a point on my graph. There's no way this equation is ever satisfied, so I cannot do that. I cannot do that either. I cannot do that either. I cannot do that either. None of these angles that I chose to plot could be a part of my graph. None of these angles could have any parts of my graph in that direction. So how do I figure it out? Maybe I revert my table, right? Maybe I do r and theta. Maybe I do r equals 0, 1, 2. And what's the theta that I'll get? Well, theta is always pi over 3. always pi over 3, always pi over 3. So what is happening on this graph? If I look at the direction pi over 3, and I think I've counted this before, each little sector in my polar grid is pi over 12, which means that to get a pi over 3, I need 4 of these. So all of this is going to be a pi over 3 right here at this angle. 1, 2, 3, 4. I will get a pi over 3. This is pi over 3. Okay. Then multiple r's with the same theta will be part of my curve. So I gotta stay on this direction. I can get something here, something here, something here, something here. I can also walk backwards. So I could go here, 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 right? So as I choose, even r's in between, negative r's, 0.5 r's, r equals 0.1, r equals 0.73, whatever. All of those r together will trace out this line. So this equation, theta equals pi over 3, is a line that goes through the origin and has slope equals tangent pi over 3. So the angle between that line and the x-axis is pi over 3. So that's actually pretty cool. It's also a very simple equation. Whenever you have a line that goes through the origin, it will also have a very simple equation in polar coordinates, just like circles. It's not a coincidence that the polar grid is made out of circles, just like the one we graphed before, and lines, just like the one we graphed just now. So it's not a coincidence. These have very, very simple equations. So if you want to obtain a Cartesian a Cartesian equation to check your work, you can remember that tangent theta equals y over x. So that means tangent pi over 3 is y over x. What's the tangent of pi over 3? You got to go back to your table of angles if you need to. You got to go 1, 2, 3, 3, 2, 1, square root 3, everything over 2, square root for each one, square root 3 over 3, 1, square root 3, and pi over 3 has tangent equals to the square root of 3, like this. So as you move this x over, your equation becomes y equals root 3x. And if you remember, this is exactly what the slope-intercept equation of a line is supposed to be. Y equals mx plus b, m being the slope, b being the y-intercept. So the y-intercept is 0 because there's no b, there's no plus anything after the x, and m is 3 is the slope of my line. So it's exactly what is expected on this problem. Sometimes, as you kind of saw here, you need a lot more points to decide what your curve is going to look like. I'm going to plot a few of these. You'd never have to plot all of them in a problem unless whoever is asking the question, if the problem asks you to, you do need to do that. Ask and plot however many the problem tells you to plot, right? But right here, I put all of this table, this entire table with, this is the most amount of points I would ever ask you to plot, and I probably won't ask you to plot this many. My general rule of thumb is just plot as many as you need to make a decision. Yeah. So I have r equals to 2 cosine theta right here. So I need to start calculating cosines and sines of those angles, walk or move in the direction of those angles, whatever r tells me to, okay? So whenever r is 0, theta is 0, cosine of 0 is 1. So in the direction of 0, when I plug that in, r equals 2 times 1, so 2. So r is going to be 2. I'll be moving 2 units in this direction. I'll be at this point, yes? When I'm at pi over 6, then I'm going to do r equals 2 cosine pi over 6. What's the cosine of pi over 6? That's the square root of 3 over 2. So this will be the square root of 3. So at pi over 6, remember I said each of those little sectors is pi over 12. So with 2 of these, I get pi over 6. So I'll be moving in this direction. Root 3. Root 3 is about 1.7 if I'm not mistaken, which means you're not going to be quite at 2. So you're not going to go all the way here. Sorry, you're not going to go all the way here. You're going to be a little bit before, maybe right here. It's about 1.7. And so this is one of the issues for certain equations. You kind of have to start estimating, and it gets more complicated. I'm going to plot a few more until I'm satisfied with the shape that this draws. So whenever theta is, so this is root 3, which is about 1.7, and theta is pi over 4, right, the cosine of pi over 4, which would be then 2 square root 2 over 2, which is the square root of 2, which is about 1.4. So this is root 2, which is about 1.4. So we're in the direction of pi over 4, which means we're halfway in between, and we're a little closer to the origin than we were in the previous step, right? Let's keep going. Let's draw a few more until I'm happy. Let's try pi over 3. Theta equals pi over 3. So that will be, theta equals pi over 3 will be 2 cosine pi over 3. That will be r. Cosine pi over 3 is 1/2. So this will be 2 times 1, 2 times 1/2, which will be 1. So in the direction pi over 3, and again, you have pi over 12s here, right? And so to get pi over 3, you need 4 of these. So you need 1, 2, 3, 4. You're going to be pointing this way right here. And then you're going to be moving 1 unit only. So you're going to end up right here. Yes. So this is 1. And at pi over 2, and this is the last one that I'll plot, and I'll tell you why in a second. Theta equals pi over 2. R will be 2 cosine pi over 2. The cosine of pi over 2 is 0. So theta will be 0. That means we're going to look up, but then we're going to move 0 units. We're not going to move at all. We're going to stay right here. So if you look at this shape carefully, you can see that it traces something like this. And you can also note that the cosine function is, or remember that the cosine function is an even function, meaning when I plot the negative angles right here, I'm going to get the same values that I got for the positive angles. So whenever I'm here on the 4th quadrant, which would be this part of the graph, yes, I'm going to get the same values, but now backwards I'm going to get 0, 1, root 2, and root 3. Have I skipped something? Yes, I've skipped the 2 right here, so I'm going to fix that. This is going to be, again, you can check this if you want on your own. I think it's actually a good idea for you to do that, but I'm saying that whatever shape I got above here, I'll also get a reflection of this below. This is what I'm saying, and you can double check the values on your own if you'd like. And you can see this is going to be a circle. Do you need to plot these? Will I get different points if I plot these? I'll let you check these by hand yourself, but because of the way that the cosine works with negative values for certain angles, if you look this way, you're going to get a negative value that's going to end up sending you over the other side. If you look this way, you're going to get a negative value that's going to end up sending you over the other side. So you're going to be just tracing the circle twice as you go through all values of theta. How can I make sure that this is in fact a circle, or maybe if I'm only making a sort of assumption here and this is not really a circle, I'm hoping that it's a circle, so I'm making things look like circles. So I'm going to take this equation, r equals 2 cosine theta. So r equals to 2 cosine theta, and I'm going to remember two things. I know r squared. This is my equation, and I know r squared is x squared plus y squared, and I also know that r cosine theta is x. So with those two things in mind, what can I do to this equation on the left to get these two pieces here so that my equation looks a little bit better? If I multiply both sides of this equation on the left by r, I'm going to get r squared equals to 2r cosine theta. So I'll get x squared plus y squared equals 2x. Take a second to look at this. And then spoil the last example there. X squared minus 2x plus y squared equals 0. I can complete the square. If you remember how that's done, you divide this by 2 to get a 1 negative, and then you square that to get a 1 positive. Add here, so you gotta add that number to both sides to keep the equation balanced. Let me move this equation further down so I can finish my example. And then with this new equation, I'm going to get x minus 1 squared equals y squared, plus y squared, equals 1. That is telling me that this is exactly a circle centered at the point 1, 0 with radius 1. If you go back to my sketch, this is exactly what we have, the center of the circle being somewhere right here. And the radius you can see is this distance there. So this is exactly confirming what our plotting did. Okay. So sometimes things get a little bit more complicated than this. Just reading this problem, take a second to read it. You're going to see, first of all, that the wording is slightly off. It doesn't say use the Cartesian equation to confirm your graph, to confirm what you found. So that's not going to help us much. But we're still going to try and find a Cartesian equation if we can for this. Now, how can I possibly trace this? Let me go ahead and copy the table, bring it down. I'll be using this one, erase what I had, and plot new values. I'm not going to use all of those values. Let me also copy the grid. I'm not going to use all of these values, but I know these are all values that I can use if I need to. So I'm going to keep this on my table. You don't have to use them all, like I said. All right, so I will start with the quadrantal angles, being the 4 angles that divide the quadrants. So 0, pi over 2, pi, 3 pi over 2. So I'm going to use these guys first, just to see if they give me an idea of what to sketch, and then I'll go from there. So I'm going to go ahead and see what happens when theta equals 0. That will be 1 plus sine of 0. So 1, which means we're moving 1 in the positive x direction. This is 1 point on my curve. When theta is pi over 2, r is 1 plus sine pi over 2. Sine pi over 2 is 1. So theta, r is 2, excuse me. So I have 2 in this direction. This is already not looking very much like a circle. Maybe it's going to loop out this way, I don't know, but we'll see. Theta equals 3 pi, sorry, pi first, correct? R equals 1 plus sine pi. The sine of pi is 0, so R is 1. That's another one. I'll look at pi. I'm looking straight to the left here. My angle is pi. So it's not going to loop out this way. It's looking like it's going to do this somehow. Yes. And then next, I'm going to see what happens to 3 pi over 2. I have 2 pi's in here just to make the tables have the same size. And so each of the 2 tables gives me half of the curve, or half of the polar plane. But I have 2 pi's, so I don't have to do that calculation again. And now I'm going to do 3 pi over 2 for theta. And so this is going to be R equals to 1 plus sine 3 pi over 2. And if you remember your unit circle, this is going to be 1 minus 1. So R is going to be 0. So we're facing this way, but R is 0, so it's telling us to not move at all. We stay where we are. So this is looking kind of weird. You can plot some points in between if you feel like, but what I will say is that you're getting positive sine values or positive values here. You're never getting negative values for R. Just look at this. Sine could never be less than -1 for it to cancel out this +1. So the least you could possibly get is 0, which happens exactly at 3 pi over 2. So you're traveling this way on the first, when you go from this angle to this angle, you're changing from 1 to 2, and then changing back from 2 to 1, and then you're changing from 1 to 0. So your distance is going to decrease. You're going to look this way, it's going to be a little less. You're going to look this way, it's going to be a little less, a little less, a little less, until you close all the way to 0. Yeah. You can, again, enter some values to convince yourself of this fact, but you're going to get a curve that looks like this, sort of like an upside down heart, and you can rotate this heart 90 degrees any way. You can make it upside, can make it upright. But this type of curve is called a cardioid because it traces this cute little heart in either direction. One thing that you can do sometimes to double check that your work is correct is to use something like Desmos's graphing calculator and literally just type in the equation. So I can just put it here, just put an R, an equal sign, and I can do 1 plus, and just type in sine, S-I-N, and theta, T-H-E-T-A. As I hit enter, it should trace out the cardioid. My screen is kind of overworked here, but you can kind of see that it traces out the correct curve. You can do that yourself. On the left here, you can kind of see that theta is bound between 0 and 2 pi. If you wanted pieces of that curve, you could also change that and maybe make theta between certain intervals. You'd only take a piece of the cardioid. So I think that's also pretty cool. But I hope this helped you trace curves, polar curves, using tables. This is not the only way, as I've said. We're going to be using graphs of the sine and the cosine function sometimes to be able to graph polar curves differently. So this is going to be all for this video. I'm going to talk about a different way in the future.